You know that the human ear cannot hear sounds of all frequencies. The range of frequencies of sound waves to which the human ear is sensitive is known as the audible range. This audible range is normally from 20 Hz to 20,000 Hz. In the same way, the human eye is also not sensitive to all frequencies of electromagnetic waves. The electromagnetic waves to which the human eye is sensitive is called visible light. The approximate frequency range of visible light is 4 into 10 power 14 Hz to 7 into 10 power 14 Hz. In terms of wavelength, the range of visible light is 700 nanometer to 400 nanometer. All electromagnetic waves, including light waves, travel in vacuum with an approximate speed of 3 into 10 to the power of 8 meter per second. This, in fact, is the limiting speed of nature. That is, in a vacuum, no other wave or particle can travel with a speed that is greater than the speed of light. When the size of an object with which light interacts is very large compared to its wavelength, we can treat the light traveling in straight line. This straight path of light is called a ray of light. A bundle of such rays together is called a beam of light. The study of different optical phenomena by treating light as rays is known as ray optics. In ray optics, the propagation of light through an optical media is studied by tracing these light rays. Let us first observe the path of light when it falls on an interface of two transparent media. When a beam of light is incident on an interface separating two transparent media, it is partly transmitted through the second medium and partly reflected into the same medium. The light ray that falls on the interface of the two media is called an incident ray. The light ray that is transmitted through the second medium is called a refracted ray. The light ray that bounces back to the first medium is called a reflected ray. The angle between the incident ray and the normal is called angle of incidence, I. The angle between the reflected ray and the normal is called angle of reflection, theta. The angle between the refracted ray and the normal is called angle of refraction, R. You may have observed that when light rays enter the second medium, they deviate from their usual path. This phenomenon is known as refraction of light, and you will study this in detail in subsequent modules. If the second medium is opaque, most of the light reflects back to the same medium. When the surface is smooth, reflection takes place at a definite angle and is known as specular reflection. If the surface is rough, reflection is called diffuse reflection. Whether the reflection is specular or diffuse, it was experimentally found that the reflection of light follows two laws known as the laws of reflection. According to the first law, the angle of incidence I is equal to the angle of reflection theta. The second law says that the incident ray, the reflected ray, and the normal to the surface at the point of incidence all lie in the same plane. These laws of reflection are valid in the case of curved surfaces also. We need to draw a normal to the surface of point of incidence to measure the angle of incidence I and the angle of reflection theta. This can be done by first drawing a tangent to the curve at the point of incidence, and then by drawing a normal to the tangent at that point. Now take a look at the picture. We can see the image of hilltops on the smooth surface of water. It is like any image we see in a plane mirror. But what is an image? When a point object O is placed in front of a plane mirror, rays from the object after falling on the mirror get reflected and form a diverging beam. If these diverging rays are extended backward, they meet at a point, say I. That is, the diverging beam of light appears to be coming out of a point I behind the mirror. This point I is the image of the point object O. This is a virtual image because after reflection, the rays appear to be diverging from that point. If a converging lens is placed between the object and the mirror, light rays, after passing through the lens, form a converging beam. When this converging beam of light is incident on the plane mirror, after reflection, they converge to a point and form an image IR. Since the image is formed by actual convergence of light to a point, it is known as a real image. Hence, we have two types of images, real and virtual images. When light rays from an object, after reflection or refraction, actually meet at a point and form an image, it is called a real image. If the light rays after reflection or refraction appear to diverge from a point, the image is called a virtual image. You have already learned about plane mirrors. But mirrors are not always flat. Take a hollow glass sphere and cut a small portion out of it. The inner hollow surface of this cut portion is called the concave surface, and the outer bulging surface is called the convex surface. If the convex side is given a silver coating, and the smooth concave surface acts as a reflecting surface, the mirror is called a concave mirror. On the other hand, if the concave surface is coated in silver and the smooth convex surface acts as a reflecting surface, the mirror is called a convex mirror. Let us define certain terms relating to spherical mirrors. The center of the sphere of which the mirror is a part is called the center of curvature, C. And the radius of the sphere is the radius of curvature, R. The geometrical center of the spherical mirror is called its pole. The imaginary line passing through the pole and the center of curvature of a mirror is called the principal axis. If rays of light from an object make small angles with the principal axis and incident at points close to the pole. The rays are called paraxial rays. Paraxial rays, parallel to the principal axis, after reflection from a concave mirror, converge to a point on the principal axis. This point of convergence is called the principal focus of the concave mirror. In the case of a convex mirror, such parallel rays of light after reflection appear to diverge from a point on the principal axis, known as the principal focus of the convex mirror. When parallel rays making a small angle with the principal axis are incident on a concave mirror, the rays converging to a point on a plane that is normal to the principal axis and passing through the principal focus. This plane is called the focal plane. The distance between the pole and the principal focus of a mirror is called its focal length and is denoted by f. Now let us derive a relationship between the focal length f and the radius of curvature r of a mirror. Consider a ray of light parallel to the principal axis incident on the mirror at a point M. We know that the ray of light, after reflection, passes through F in the case of a concave mirror and appears to diverge from F in the case of a convex mirror. Since C is the center of curvature of the mirror, CM is the normal to the mirror at M. If the angle of incidence is theta, then the angle of reflection is also equal to theta. Let MD be the perpendicular to the principal axis through M. Using basic laws of geometry, we can write that angle MCD is equal to theta and the angle MFD is equal to 2 theta. From the triangle MCD, tan theta is equal to MD by CD. Let this be equation 1. And from the triangle MFD, tan 2 theta is equal to MD by FD. Let this be equation 2. For paraaxial rays, theta is small and hence we can write tan theta is approximately equal to theta. Let this be expression 1. And tan 2 theta is approximately equal to 2 theta. Let this be expression 2. From expressions 1 and 2, we can write that tan 2 theta is equal to 2 into tan theta. On substituting the values of tan theta and tan 2 theta from equations 1 and 2, we get MD by FD is equal to 2 into MD by CD. Or CD is equal to 2 into FD. Let this be equation 3. For paraxial rays, the 2 points P and D are very close to each other. And hence, we can assume that CD is equal to CP. And FD is equal to FP. Therefore, CP is equal to 2 into FP. This equation can also be written as PC is equal to 2 into PF. But PC is the radius of curvature R and PF is the focal length F. Therefore, R is equal to 2F. Now let us study the images formed by spherical mirrors. The following 4 rays from the source are easy to trace and help locate the images formed by a spherical mirror. 1. If the incident ray is parallel to the principal axis, then, after reflection, it passes through the principal focus in the case of a concave mirror and appears to diverge from the principal focus in the case of a convex mirror. 2. If a ray of light initially passes through or appears to pass through the center of curvature C, then, after reflection, the ray retraces its path. 3. If a ray of light initially passes through or appears to pass through the principal focus F of the mirror, then, after reflection, the ray is parallel to the principal axis. 4. If a ray of light is incident at the pole, then the incident ray and reflected ray make identical angles with the principal axis. Let us place an object AB in front of a concave mirror. Using the rays of light discussed, we can find the image of point B at point B dash. Not only these 4 rays, any ray that emerges from B and incident on the mirror after reflection passes through point B dash. By treating object AB as a combination of many point objects and by finding the images corresponding to each of these point objects, we can find the image of the whole object AB as A dash B dash. Thus, the image of an extended object has a point-to-point correspondence with the object. Images formed by a concave mirror for different positions of an object are as shown. Similarly, in the case of a convex mirror, for different positions of an object, the images formed are as shown. Usually, the distance of the object from the mirror is denoted by U, and the distance of the image from the mirror is denoted by V. We follow the Cartesian sign convention to measure distances from the mirror and heights from the principal axis. According to this convention, all distances are measured from the pole of the mirror. For example, measurement of the focal length F and the radius of curvature R are measured as shown. Distances in the direction of incident light are taken as positive, and distances measured in the direction opposite to the direction of incident light are taken as negative. For example, in the case of a concave mirror, if the focal length and the radius of curvature is measured from the pole, then the measurement is in a direction opposite to the direction of the incident light. Hence, they must have negative values. On the other hand, for a convex mirror, the values of focal length and radius of curvature must be positive, as these measurements are in the same direction as the direction of the incident ray. Heights measured upward and normal to the principal axis are taken as positive, and the heights measured downward are taken as negative. When object AB is placed beyond C of a concave mirror, an inverted image A'(B' is formed. In such a case, the length of the object is positive and the length of the image is negative. With the proper sign convention, we can use a single formula which we will discuss in the next module for all possible cases. The mathematical relationship between an object distance u, image distance v, and the focal length f of a mirror is called the mirror equation. Let us derive the mirror equation for a specific case where the object is placed beyond C of a concave mirror. Let OJ be the object and IG be its image. If only paraxial rays are considered, M must be very close to P, and hence PM can be treated as a straight line. And OJ is equal to PM. Now observe the ray diagram. As triangles IGF and PMF are similar, we can write IG by PM is equal to IF by PF. Since PM is equal to OJ, this can also be written as IG by OJ is equal to IF by PF. Let this be equation 1. Now, observe the two triangles OJC and IGC. Since they are also similar triangles, we can write IG by OJ is equal to IC by CO. Let this be equation 2. From equations 1 and 2, we can write IC by CO is equal to IF by PF. Let this be equation 3. But from the ray diagram, we can write IC is equal to PC minus PI, where CO is equal to PO minus PC and IF is equal to PI minus PF. Substituting these values in equation 3, we get PC minus PI whole divided by PO minus PC is equal to PI minus PF whole divided by PF, which is equal to PI by PF minus 1. On simplification, we get PI by PF is equal to PO minus PI whole divided by PO minus PC. Let this be equation 4. We know that PO is the object distance, PI is the image distance, PF is the focal length, and PC is the radius of curvature. Now we need to apply the Cartesian sign convention to substitute appropriate values for these terms. Note that the object is to the left of the mirror, and hence the light rays are incident on the mirror from left to right. Hence, the direction from left to right is to be taken as positive. Now, on application of the Cartesian sign convention, we can write that PO is equal to minus U, PI is equal to minus V, PF is equal to minus F, and PC is equal to minus R, which is also equal to minus 2F. On substituting these values in equation 4, we get Equation 5. On further simplification, we get UV is equal to UF plus VF. Dividing each term of this equation with UVF, we get 1 by F is equal to 1 by V plus 1 by U. This is known as the mirror equation. This equation is valid for both types of spherical mirrors and is applicable to all positions of the object. It is important to note that, while using the mirror formula, proper use of a sign convention is required. We know that the size of the image formed by a spherical mirror depends on the position of the object. The ratio of the height of the image to the height of the object is defined as the linear magnification and is denoted by M. If H is the height of the object and H dash is the height of the image, then M is equal to H dash by H. Since the two triangles OJP and IGP are similar, we can write that IG by OJ is equal to PI by PO. When a proper sign convention is applied, we get OJ is equal to H and IG is equal to minus H dash. Substituting these values in the above equation, we get minus H dash by H is equal to minus V by minus U. Therefore, M is equal to H dash by H and is equal to minus V by U. Note that the linear magnification M is negative if the image is inverted. And as a consequence, M is negative in case of real images. On the other hand, if the image is erect, M is positive. Hence, M is positive for virtual images. Now let us use the mirror formula and the expression for linear magnification to solve some problems. Example 1. A plane sheet of length 0.1 meter and breadth 0.05 meter is placed at a distance 0.25 meter from a concave mirror of focal length 0.2 meter. If the principal axis of the mirror is perpendicular to the plane of the sheet and passes through one of the vertices, then find the length and breadth of the image formed. Solution. Given that length of the sheet L is equal to 0.1 meter, breadth of the sheet B is equal to 0.05 meter, object distance U is equal to minus 0.25 meter, focal length F is equal to minus 0.2 meter. According to the mirror formula, 1 by F is equal to 1 by V plus 1 by U. This can be written as 1 by V is equal to 1 by F minus 1 by U. Substituting the values for U and F, and on simplification, we get V is equal to minus 1. That means the image is formed at 1 meter from the mirror. We know that magnification M is equal to minus V by U. On substituting the values for U and V, and on further simplification, we get M is equal to minus 4. That means the image is 4 times bigger than the object. Note that the minus sign for magnification M indicates that the image formed is inverted. Now the length of the image L dash is equal to M into L, which is equal to 0.4 meter. And the breadth of the image B dash is equal to M into B, which is equal to 0.2 meter. Example 2. The image formed by a convex mirror of focal length 0.4 meter is 1/4 the size of the object. Find the distance of the object from the mirror. Solution. Given that the focal length f is equal to 0.4 meter and magnification m is equal to 1/4, we need to find the object distance u. F is positive because we are dealing with a convex mirror. Since a convex mirror always forms an erect image, m is taken as positive. We know that m is equal to minus v by u. According to the mirror formula, 1 by f is equal to 1 by v plus 1 by u. This can be written as 1 by v is equal to 1 by f minus 1 by u. Or 1 by v is equal to u minus f by uf. Implies v is equal to uf by u minus f. Or v by u is equal to f by u minus f. This can be written as minus v by u is equal to f by f minus u. Or m is equal to f by f minus u. Substituting the values for f and m in this equation and on further simplification, we get u is equal to minus 1.2 meters. Note that u is negative because the object is always in front of the mirror. Example 3. When a concave mirror is used, the magnification is found to be 4 times greater than when the object was 0.25 meter from the mirror as it was with the object at 0.4 meter from the mirror. If the image formed is real in both cases, find the focal length of the mirror. Solution. Since the images are real, both the magnifications are negative. Let the magnification be minus m1 when the object is at a distance of 0.4 meter and minus m2 when the object is at a distance of 0.25 meter. On rewriting the mirror equation, we have m is equal to f divided by f minus u. Then, m1 is equal to f divided by f minus u1 and m2 is equal to f divided by f minus u2. Now we can write minus m2 is equal to 4 into minus m1. That can also be written as m2 is equal to 4 into m1. On substituting the values of m1 and m2 from the above equations and on further simplification, we have 3f is equal to 4u2 minus u1. When the values of u1 and u2 are substituted, we get f is equal to minus 0.2 meter. How does one solve the problem if the second image is a virtual image? If the second image is virtual, then M2 is positive. Then we will get the condition as M2 is equal to 4 into minus M1. And by substituting the values for M1 and M2 and on further simplification, we get f is equal to minus 0.28 meter. Can we solve the same problem if both the images are virtual? To get virtual images, in both cases, the object must be between F and P. As the object is moved from F to P, the size of the virtual image decreases. As such, the condition M2 is 4 times M1 cannot be fulfilled. Let us study the refraction of an obliquely incident ray of light through a parallel-sided glass slab. In such cases, light gets refracted at two interfaces. First, the ray of light is incident on the air glass interface and refracts through the glass slab. Let the angle of incidence be I and the angle of refraction be R. If the refractive index of glass with respect to air is NGA, then, according to Snell's law, NGA is equal to sin I by sin R. Let this be equation 1. The refracted ray is then incident on the glass-air interface and refracts to air. For glass-to-air refraction, the angle of incidence is equal to R. Let the angle of refraction be theta. If the refractive index of air with respect to glass is NAG, then, according to Snell's law, NAG is equal to sin R by sin theta. But we know that NGA is equal to 1 divided by NAG. On substituting the values of NGA and NAG from equations 1 and 2, and on further simplification, we get angle I is equal to angle theta. This means the emergent ray is parallel to the incident ray, and hence there is no deviation for the incident ray. But note that the light ray has displaced laterally from its original path. The perpendicular distance between the incident ray and the emergent ray is known as lateral shift. The value of lateral shift depends on certain factors like angle of incidence, thickness of the glass slab, refractive index of the medium, and wavelength of the incident ray. Lateral shift increases with an increase in the angle of incidence. Thickness of the glass slab and the refractive index of the medium. Since the refractive index of a medium is inversely proportional to the wavelength of the incident light, lateral shift also is inversely proportional to the wavelength of the incident ray. Let us consider an example. Example 1. A ray of light is incident on a rectangular glass slab of thickness √3 cm at an angle of 45 degrees. If the refractive index of the glass is √2 for the incident light, what is the lateral shift of the emergent light ray? Let PQ be a ray of light ray incident on a glass slab of thickness √3 units. RS represents the emergent ray. QM is the normal to the surface at Q, and PQT represents the path of the incident ray if there were no glass slab. RT represents the lateral shift of the light ray. Given that the angle of incidence I is equal to 45 degrees and the refractive index of the medium is √2. From Snell's law, we have N is equal to sin I by sin R. Substituting the values of N and I, and on further simplification, we get R is equal to 30 degrees. From the triangle QMR, cos R is equal to QM by QR. But QM is the thickness of the glass slab and is equal to √3 units. On substituting these values and on further simplification, we get QR is equal to 2 centimeters. In the triangle QTR, angle TQR is equal to I minus R and is equal to 15 degrees. From the triangle QTR, sin I minus R is equal to TR by QR. TR is equal to QR sin I minus R. On simplification, we find the lateral shift TR is equal to 0.52 centimeter. Now, let us try to reason a common observation that the apparent depth of a transparent material like glass or water when viewed from above is less than the actual depth. Consider a point O at the bottom of a container filled to a depth of h with a liquid of refractive index n. Let OA be a light ray that strikes the liquid-air interface normally and hence travels without any deviation. Consider another light ray, OB, close to OA. Since OB travels from a denser to a rarer medium, it bends away from the normal MM- and forms a ray BC. The ray BC appears to diverge from O'. Then, O' is the image of O and AO' is the apparent depth of the liquid. Say H'. This means when an object in a denser medium is viewed from a rarer medium, the apparent position of the object is closer than its real position due to refraction. Let the angle of incidence OBM be I and the angle of refraction M-BC be R. Since the two angles OBM and AOB are alternate angles, they are equal. Similarly, since the two angles AO'-B and M'-BC are corresponding angles, they are also equal. Then from triangle OAB, tan I is equal to AB by OA, which is equal to AB by H. And from triangle O-AB, tan R is equal to AB by O-A and is equal to AB by H-. Therefore, tan I by tan R is equal to AB by H divided by AB by H-, which is equal to H' by H. Since the 2 points A and B are close to each other, angles I and R are very small. Hence, tan I and tan R are approximately equal to sin I and sin R. But according to Snell's law, sin I by sin R is equal to 1 by n. Therefore, n is equal to h by h', or the refractive index is equal to real depth by apparent depth. Consider the following example. Example 2. A glass slab of thickness 0.30 meter is placed on a table. Find the apparent shift of a point on the table when seen through the glass slab. Assume the refractive index of glass is 3 by 2. Let P be a point on top of the table and P' be its image when seen through the glass slab. Let the actual depth of point P be h and its apparent depth be h'. Then, the shift in the position of P is h minus h'. We know that the refractive index n of the glass is equal to h by h'. This can also be written as 1 by n is equal to h' by h. On further simplification, we get shift is equal to h into 1 minus 1 by n. Given that h is equal to 0.30 meter and n is equal to 3 by 2, substituting these values in the above equation and on further simplification, we get the shift as 0.10 meter. Now let us study the effects of atmospheric refraction. The density of atmospheric air is not uniform. It is maximum at the surface of the Earth and decreases with an increase in altitude. Even the refractive index of atmospheric air is maximum at the surface of the Earth and minimum at the outermost layer of the atmosphere. When an oblique light ray from a heavenly body like the Sun enters the atmosphere, it continuously moves into regions of high refractive index and hence bends towards the normal. This bending of light through atmospheric air is known as atmospheric refraction. When the Sun is directly overhead, atmospheric refraction is 0, as the Sun's rays are incident normally. When the Sun is on the horizon, atmospheric refraction is more predominant. This is because when the Sun is on the horizon, light rays have to travel longer distances through the atmosphere. Knowledge of atmospheric refraction is useful in understanding some natural phenomena. The apparent position of any heavenly body is a little above its actual position with respect to an observer on earth. Observe how the apparent position changes with a change in the actual position of the sun. When the sun is just below the horizon, the apparent position is a little above the horizon. Due to this, the sun is visible about 2 minutes before actual sunrise and 2 minutes after sunset. At the time of sunrise and sunset, the sun appears to have an oval shape. The rays from the lower region of the sun travel longer distances than rays from the upper regions. As a result, the upward shift is more for the lower end and the sun appears oval. The twinkling of stars is also due to atmospheric refraction. Due to winds and other climatic changes, the density of some regions in the atmosphere may change with time. The intensity of light from the stars is low. If these rays happen to pass through regions of the atmosphere with a continuous change of density, then the image of the star changes its location and causes twinkling. In the earlier modules, we have seen how light refracts through a plane interface of two transparent media. The laws of refraction are applicable even when the interface separating the two transparent media is spherical in shape. Now let us study the refraction of light at a spherical surface in detail. Let C be the center of curvature of the spherical surface, AB be the principal axis, and P be the point of intersection of the spherical surface and the principal axis. If a ray of light is incident on the spherical surface, it refracts to the second medium. In order to apply the laws of refraction, we need to draw a normal to the spherical surface at the point of incidence. Normal to the spherical surface at any point can be drawn by joining the point to the center of curvature C. For example, if P, M, and N are three different points on the spherical surface, then PC, MC, and NC are the three normals at the 3 points mentioned. Let us assume that the first medium is optically rarer compared to the second medium, and place a point object O on the principal axis in the rarer medium. Now consider the light ray OP. Since it is incident normally on the spherical surface, the ray OP propagates to the denser medium without any deviation. Whereas, rays like OM and ON, after refraction, bend towards the normal because they pass from a rarer to a denser medium. All the refracted rays converge to a point on the principal axis and form a point image I. Here, PO is the object distance U and PI is the image distance V. And if the radius of curvature is R, then PC is equal to R. Before we derive a relationship between the object distance and image distance, You need to know about the Cartesian sign convention we follow in case of refraction at a spherical surface. This is similar to the one you learned in the case of mirrors. The conventions are: 1. All measurements are made from the point of intersection of the spherical surface and the principal axis. 2. Measurements are taken as positive if they are in the direction of the incident light, otherwise they are taken as negative. 3. Lengths measured upwards are positive. They are negative if measured downwards. Let us now derive an object-image relationship for a spherical surface. Let the refractive index of the rarer medium be N1 and the refractive index of the denser medium be N2. If the aperture of the spherical interface is small when compared to the object distance u and the image distance v, then the following approximations can be made. 1. Arc PM can be taken as a line perpendicular to the principal axis. 2. The angle of incidence and the angle of refraction are very small, and hence tan and sine functions of these angles are approximately equal to the respective angles. Let the angle MOP be theta 1, angle MCP be theta 2, and angle MIP be theta 3. Then, tan theta 1 is equal to PM by PO, tan theta 2 is equal to PM by PC, and tan theta 3 is equal to PM by PI. Since the angles are small, tan theta 1, tan theta 2, and tan theta 3 are approximately equal to theta 1, theta 2, and theta 3 respectively. Then we can write that theta 1 is equal to PM by PO, theta 2 is equal to PM by PC, and theta 3 is equal to PM by PI. For the triangle MOC, I is the exterior angle and is equal to the sum of the two interior angles theta 1 and theta 2. This can be written as I is equal to PM by PO plus PM by PC. Let this be equation 1. Similarly, for the triangle MIC, theta 2 is the exterior angle and is equal to the sum of R and theta 3, or R is equal to theta 2 minus theta 3. This can also be written as R is equal to PM by PC minus PM by PI. Let this be equation 2. But according to Snell's law, sin I by sin R is equal to N21, and we know that N21 is equal to N2 by N1. Therefore, N1 sin I is equal to N2 sin R. For small angles, this can also be written as N1I is equal to N2R. On substituting the values of I and R from equations 1 and 2, and after further simplification, we get N1 by PO plus N2 by PI is equal to N2 minus N1 by PC. Let this be equation 3. But, on applying the Cartesian sign convention, PO is equal to minus U, PC is equal to R, and PI is equal to V. On substituting these values in equation 3, we get N2 by V minus N1 by U is equal to N2 minus N1 by R. Let this be equation 4. This equation gives a relationship between object distance and image distance for refraction at a spherical surface and is valid for all types of spherical surfaces. Let us now look at a problem. A point-sized air bubble is trapped inside a glass sphere of radius of curvature 10 cm. The air bubble is at a distance of 2 cm right of the center of the sphere as shown. If the refractive index of the glass is 1.5, find the apparent location of the air bubble when viewed from left and along the line joining it with the center of the sphere. Solution. The refractive index of the medium in which the point object is present, N1, is equal to 1.5. Since the other medium is air, N2 is equal to 1. Let B be the point of intersection of the principal axis and the spherical surface that lies in the direction of the viewer. All the measurements are to be made from B. Since R and U are measured in a direction opposite to the direction of the incident light, they are negative. Therefore, R is equal to -10 and U is equal to -12. Substituting these values in equation 4 and on further simplification, we get V is equal to -13.33 cm. Since the object is in denser medium after refraction, light rays bend away from the normal. When produced backwards, the image is formed at a distance of 13.33 cm from B. Now let us find out the apparent position of the air bubble if it is viewed from the right side. If D is the intersecting point of the spherical surface with the principal axis towards the air bubble, all measurements are made from this point. R is equal to -10 cm and U is equal to -8 cm. Substituting these values in equation 4 and on further simplification, we get V is equal to -7.28 cm. The corresponding ray diagram is as shown. We know that when a light ray passes from denser to rarer medium, it partially refracts to the rarer medium and bends away from the normal, and partially reflects back into the denser medium. This reflection is known as the internal reflection. In case of refraction from denser to rarer medium, the angle of refraction R is greater than the angle of incidence I. If another light ray with higher angle of incidence is considered, its angle of refraction will also be correspondingly higher. If the angle of incidence of the light ray is gradually increased, then for a specific angle of incidence, when the angle of refraction in the rarer medium becomes 90 degrees, the refracted light grazes along the interface. This angle of incidence in the denser medium is called the critical angle C for the pair of media under consideration. That means if I is equal to C, then R is equal to 90 degrees. Let N21 be the refractive index of the rarer medium with respect to the denser medium. Let N12 be the refractive index of the denser medium with respect to the rarer medium. We know that N12 is equal to 1 by N21. As per Snell's law, N21 is equal to sin I by sin R, which is equal to sin C by sin 90. Therefore, N21 is equal to sin C, or N12 is equal to 1 by sin C. This means the refractive index of the denser medium with respect to rarer medium N12 is equal to 1 by sin C. If the angle of incidence is made larger than the critical angle, the incident light cannot refract to the rarer medium and is completely reflected back into the denser medium. This is known as total internal reflection. Since there is no transmission of light to rarer medium, light gets completely reflected back to the denser medium. That is, it gets totally internally reflected. Hence, for light to have total internal reflection, it must satisfy the following conditions. 1. It must propagate from denser medium to rarer medium, and 2. The angle of incidence must be greater than the critical angle for the pair of media. Observe how light refracts through a glass-air interface for various possible angles of incidence. Let us look at some examples and applications of total internal reflection. Formation of mirage and the sparkling of a diamond is due to total internal reflection. The illusion of the presence of water on a hot summer day at a distance is known as mirage. The images of the nearby objects give the impression that there is a pool of water, but this in reality is an optical illusion. During a hot summer day, the layer of air nearest to the surface of the earth is hottest. And as we move up the ground, we come across layers of air with decreasing temperature. As a result, the refractive index of different layers of air increases as we move up. And hence, layers of the hot air near the Earth's surface are optically rarer than the layers of the cold air a little above it. Due to this, rays from the nearby objects which are propagating towards the Earth's surface refract and bend away from the normal. At some point, the angle of incidence exceeds the critical angle and the rays undergo total internal reflection. An observer is able to see the image and get the impression of a mirage. Another example of total internal reflection is the sparkling of diamond. Diamond has a high refractive index of 2.42 and the critical angle for the diamond-air interface is 24.4 degrees. Diamonds are cut in such a way that most of the light rays entering the diamond undergo total internal reflection many times before they exit. This gives diamonds their bright sparkle. Total internal reflection is made use of in some technological applications also. In many optical instruments, prisms are used to deflect and redirect the light without loss of intensity. Right-angled prisms are most commonly used for such applications. A right-angled prism, whose critical angle is less than 45 degrees, can be used to deflect light at a right angle. Light incident normally on side AB passes without deviation and incident on side AC at an angle 45 degrees. Since the angle of incidence is greater than the critical angle, the light is totally internally reflected and is deviated from its original path by 90 degrees. If light is incident normally on the side AC, it travels straight and hits side AB. Then, light is internally reflected twice at surface AB and BC and leaves the prism with a deviation of 180 degrees. In this case, the image of an object gets inverted. The same prism can also be used to obtain an inverted image of an object without changing its size. Another application of total internal reflection is in optical fibers. Optical fiber is usually fabricated from glass or quartz and consists of core and cladding. The refractive index of the core material is a little higher than that of cladding material. When light is allowed to enter the core in such a way that the angle of incidence at the core cladding interface is greater than the critical angle, it will undergo successive total internal reflections all along its path in the core. Since the loss of energy is quite small in case of total internal reflection, light can be transmitted over longer distances through optical fiber with least loss of energy. This is made use of in case of optical fiber cables used for long-distance transmission of light signals. In communication systems, optical fiber cables are used to transmit video and audio signals at the speed of light. In such cases, the electrical signals are first converted to light signals and then they are transmitted through optical fiber cables. Optical fiber has applications in medicine also. It is used by doctors to illuminate and view the internal organs such as the esophagus, stomach, intestines, etc. to get back their images, and if necessary to even carry a laser beam to the relevant spot. A rainbow that appears as a 7-colored arc in the sky is one of the most beautiful optical phenomena. An observer can see a rainbow on a rainy day only when the sun is behind her and the atmosphere before her is filled with drops of rainwater. The sunlight passing through the water drops present in the atmosphere undergo refraction, dispersion, and internal reflection to form a rainbow. If the sunlight undergoes one internal reflection in the raindrops before emerging out, then the rainbow formed is called a primary rainbow. Primary rainbow is bright and narrow with red color at the outer edge and violet at the inner edge. Let us understand the formation of a primary rainbow. Consider a ray of sunlight, AB, incident on a raindrop as shown. The sunlight refracts through the water drop at point B and is dispersed into its constituent colors. The red light with the longer wavelength is bent the least, and the violet light with the shorter wavelength is bent the most. A part of the light is then internally reflected from the back surface of the water droplet. The path of the least deviated red light is represented by BCD, and that of the violet light is represented by BC-D'. The light is again refracted when it exits out of the drop of water. It is observed that the emerging violet and red colored light makes an angle of 40 and 42 degrees respectively with respect to the incoming sunlight. Now consider another water drop just below the one considered earlier. The sunlight that enters this drop also propagates in an identical way. An observer viewing a primary rainbow receives red light from the drop at the top and violet light from the drop at the bottom and other colors from other drops located between them. This is the reason why the primary rainbow is always formed with red color at its top and violet color at its bottom. Under favorable conditions, a broader but a fainter rainbow may also be seen along with the primary rainbow. This is known as the secondary rainbow. While forming the secondary rainbow, the light rays undergo two internal reflections inside the water drop, and due to this, it is fainter than the primary rainbow. Note that the colors are reversed in the secondary rainbow with red color at the inner edge and violet color at the outer edge. This is because the observer viewing the secondary rainbow receives violet light from the water drop at the top and red light from the drop at the bottom. In the case of the formation of the secondary rainbow, the emerging red light makes an angle of 50 degrees and the violet light makes an angle of 53 degrees with respect to the incoming sunlight. Now let us study about scattering of light. Normally, we don't see the path of light. Now observe a laser beam. We are able to see its path. This is due to scattering of light by small particles of air in the path of the laser light beam. The phenomenon in which a part of the light incident on a particle is redirected in different directions is called scattering of light. When sunlight is incident on a particle, the scattering effect depends on the size of the particle and the wavelength of the light. If the size of the particle is large as compared to the wavelength of the incident light, then the particle scatters light of all wavelengths equally. For example, if white light is incident on large particles, light of all wavelengths gets scattered equally in every direction. If the size of the particle is of the order of the wavelength of the incident light, then the amount of light scattered is inversely proportional to the fourth part of the wavelength. This is known as Rayleigh scattering. When white light is incident on small particles, more of the shorter wavelengths like violet and blue get scattered. Very little of the red light gets scattered. When sunlight passes through the atmosphere, it gets scattered by the atmospheric particles. The scattered blue light is nearly 10 times the scattered red light. This scattered light of small wavelengths reaches our eye and gives us the impression that the sky is blue. Though the scattered violet color is more than the blue color, sky appears blue in color because our eyes are more sensitive to the primary color blue. If there were no atmosphere, the sky would have appeared black in color. At sunrise or sunset, sunlight has to travel through the atmospheric air for longer distances. As a result, a larger number of air particles come in its way. These particles scatter most of the blue light and make the sun look orange and red. When the water vapor in the atmosphere condenses, clouds are formed. The size of the water drops present in the clouds is much large as compared to the water molecule. Since molecules of large size scatter light of all wavelengths equally, the clouds appear white in color.